Good afternoon, everyone. My name is Anjana. I am a PhD student from INCOIS. This work is basically a part of my PhD, and it titled The Impact of Oceanic Internal Variability in Modulating the Low Frequency Variability in the Indian Ocean. This has recently got published in GRL. So I'll just start with the introduction. You all know that the Indian Ocean exhibits strong interannual to decadal variability, and this variability shows strong regional differences. For example, Levitas et al. In 2009 shows that there is a hemispheric asymmetry within the Indian Ocean, with the South Indian Ocean accumulating more heat than the Northern Indian Ocean. This figure is taken from Levitas et al. Just to show that hemispheric differences. This is the total Indian Ocean heat content, and this is North Indian Ocean and South Indian Ocean, and we can see that the upper ocean heat content is more, and upper ocean heat content and associated variability is more in the South Indian Ocean compared to that of the North Indian Ocean. And the observational and model studies suggest that these variability in the South Indian Ocean are mainly due to the Indian Ocean interior winds, then the teleconnection from the Pacific, and due to some air-sea interactional processes. In addition to all this, the oceanic internal variability arises due to the nonlinearity of the oceanic system can also cause variability in a wide range of spectrum. So the main objective of this study is to understand the role of oceanic internal variability in generating the low frequency variability in the Indian Ocean using a high resolution global OGCM. Here the term low frequency is used for interannual and longer timescale variability. And the model that we use for this study is MOM, Modular Ocean Model version 5. This is a global model with uniform 1/8 degree horizontal resolution and 42 vertical levels. Out of these 42 vertical levels, the 22 levels are confined within the top 200 meters of the water column. And we obtained two simulations from this model. One is a climatological simulation and one is a control simulation or interannual simulation. For the climatological simulation, we force the model using the core to climatological forcing and spin up the model for 175 years. And the last 50 years of the simulation is used for our analysis. And the model is further integrated using JRA 55 do interannual forcing, and the output from 1958 to 2017 is used for our analysis. And to validate this model simulation, we also use the HADI-SST data and also the Aviso sea level data. Now, this is the observed variability in the Indian Ocean. The first two panel is for SST and SLA from the observation, and this is from the model control simulation. So, this map is a standard deviation. Here the standard deviation is calculated after removing the annual cycle and then applying a 15-month low pass filter, because our aim is actually to get the interannual and longer timescale variability. And from this, if we look at the SST, we can see that there is a strong variability in the South Indian Ocean compared to that of the North Indian Ocean, except for some region in the Somali and Arabian coast. This is well captured in the model also. And if we come to SLA, it shows some difference in spatial pattern, and the strong variability in SLA is in the subtropical front region around 40 degrees south. And other than that, in the South Indian Ocean, we can divide three distinct regions. One is a thermocline ridge region, and one is a subtropical Indian Ocean between 20 degrees south and 30 degrees south, and one region with higher variability is off the west coast of the Australia. And overall, there are some difference from observation and model, but the model is quite well capturing the patterns of the observation. We also validated the model with the surface circulation and transport. I have not included that in this PPT, but the model is well validated. And here we are mainly focusing on the SST and SLA variability in the subtropical and tropical South Indian Ocean, where the role of oceanic internal variability in generating the low frequency is not much documented. Now, to estimate the relative role of the internal variability, we compare the solutions from climatological simulation and the control simulation. One thing to note here is that the climatological simulation is forced with the climatological wind. So, any variability longer than the annual period from the climatological simulation is basically due to the oceanic internal variability. And the control simulation is a total variability. So, this is the ratio of the standard deviation of SST, SLA and eddy kinetic energy. And this standard deviation is also calculated by removing the annual cycle and by applying a 15-month low pass filter. So this region where the ratio between the internal variability from climatological simulation and the total variability from the control simulation is more than 0.5 are considered largely influenced by the internal variability, because the magnitude of the internal variability exceeds 50% of the observed variability, and it is comparable to that of the atmospheric forcing. Now we found the region of active internal variability. The next question is that what caused this internal variability? For that, we conducted an energy budget analysis. This equation is taken from Chatterjee et al. 2013, in which the first term is basically the rate of change of eddy kinetic energy. And in our case, the eddy fields are basically any disturbance other than the annual cycle, because for calculating this thing, we are using the climatological simulation. And the first two terms are the horizontal and vertical advection from mean and eddy flow. In here, our mean is the annual cycle and eddy are anything other than the annual cycle. And then in C, the first two terms are basically the pressure divergence, and that is very small. And the third term is the baroclinic instability. Baroclinic instability is basically the conversion of energy from the available mean potential energy to eddy kinetic energy. And then in D, the first term is the barotropic instability, and second term is the Kelvin-Helmholtz instability. And then similarly, E and F are basically horizontal and vertical deformation of work, and then due to energy dissipation due to viscosity. And one thing to note here is that except baroclinic instability, barotropic instability, and horizontal advection, all other terms for this region is very small. So we are not considered the other terms for the analysis. And now, okay. This figure shows the seasonally averaged eddy kinetic energy. This one is for austral summer, fall, winter, and spring. And we can say that the distribution of eddy kinetic energy shows some spatial and temporal differences. Moreover, that this region of strong eddy kinetic energy collocate well with the region of strong internal variability. And if we look into this figure, we can see that throughout the year, there is a strong eddy kinetic energy in the southern branch of the SACC, south of the Madagascar, and also to some extent in the central Indian Ocean, between 20 degrees south and the 25 degrees south. And in this region, the eddy kinetic energy attains its maximum value during austral, summer, and spring. On the other hand, off the west coast of Australia, the eddy kinetic energy attains its maximum value during austral fall and austral winter. This is more clear from this bar diagram. This is basically two box averages. This west box is somewhere here between 60 degree and 80 degree, and this dark patch. And the east box is near the off the west coast of the Australia. So here we can see that in the west box, the eddy kinetic energy is maximum during the austral spring and austral summer, where in the near the Australian coast, it attains its peak value during the austral fall and austral winter. And these four are the major terms from that energy budget analysis: barotropic, baroclinic, Kelvin-Helmholtz, and advection. And we can see that the baroclinic instability is the contributing term to the eddy kinetic energy. Now we understood that baroclinic instability is which caused this internal variability in the South Indian Ocean. The next is to understand what is the dynamic mechanism behind this baroclinic instability, or what is causing this baroclinic instability. For that, we adopted a method from the previous literature by Gia et al., where they mentioned that the seasonality in the thermocline can be related to the generation of the baroclinic instability. So we also adopted the same method, and we looked at the thermocline structure in that region. In this, these are for all the months, alternative months, and the background in figure A is basically the vertical section of climatological zonal current, and the shaded and the contour is basically the temperature averaged over 60 degree east and 100 degree east, which is the west box that we shown in the previous figure. And we can see that these isotherms show strong seasonal variability, especially in the top 200 meter of the water column. And we know that from the previous slide that the eddy kinetic energy and in this region attains its maximum value during austral summer, that is say January. We can see that here these isotherms are very shallow and are confined in the top 50 meters of the water column. And also the outcropped isotherm tilt polewards south of the 25 degrees south. And this tilt in isotherm will increase the vertical density, meridional density gradient below the water column. And based on the thermal wind relation, this will increase the vertical shear in the zonal currents. So here what we can say is that in the south of 25 degrees south, the vertical shear in the eastward SICC, that is this current, and the eastward SICC associated with the tilt in the isotherm is generating a baroclinic instability. Similarly, if we look to the other seasons, we can see that the isotherms are very deep, they are well mixed and they are stable. So the baroclinic instability is less there. And if we look into the this region, this is the meridional current and off the west coast of Australia. This is averaged at 30 degrees south, and we can see that we know that the eddy kinetic energy is strong during the austral fall and winter, that is basically these two seasons. And here one more thing is that this is the time when the poleward moving Lunian current and the underlying Lunian undercurrent gets strengthened. This will increase the shear between them, and also there is a strong tilt in the isotherm. So basically we can say that along the west coast of Australia, the instability is due to the shear between the poleward Lunian current and the underlying Lunian undercurrent associated with the tilt in the isotherms. Now a question will arise whether this baroclinic instability can grow in a time scale and can grow at an interannual and longer time scale and generate low frequency variability. The answer is yes. Actually, Gia et al. In 2011 already stated that the instability owing to the vertical shear can grow at a wide range of spectrum, but they are associated with a preferred zonal and meridional length scale. They already showed that the instability can grow rapidly with a smaller zonal length scale and a larger meridional length scale. On the other hand, the instability can also grow slowly at an interannual to longer time scale with a much larger zonal length scale and a smaller meridional length scale. In our case, the region of strong baroclinic instability is much narrow in the meridional direction compared to that of the zonal extent. So what we can say is that the baroclinic instability driven internal variability in the low frequency spectrum in the SIO is likely due to the preferentially growing instability mode. Now we try to find out how this instability is propagating from one place to another place. So this is basically the sea level anomaly taken from MOM climatological simulation, and this SLA is bandpassed between 1.5 to 10 years. And this homular diagram is for the first one is at 25 degrees south and the second one is at 30 degrees south. And this figure is a theoretical propagation speed of the Rossby waves and their modes, first and second modes. Now we can say that in both the latitudes there is an evident Rossby wave propagation, and this propagation speed of the Rossby waves calculated from this figure matches well with the theoretical speed of the theoretical propagation field of the speed of the Rossby waves. And one more interesting thing is that if we look here, this is at 25 degrees south, we can see that an evident Rossby wave or a strong Rossby wave propagation is in the east of the 80 degree east, whereas here it is in the west of the 80 degree east. This actually matches well with this figure. If we see at 25 degrees south, the eddy kinetic energy is high in the east of the 80 degree east, but at 30 degrees south it is in the west of the 80 degree east. Now that is all about it. So we can say that the slowly growing baroclinic instability matches the scale of lower order modes of Rossby waves, and they propagate westward carrying the energy from the eastern part of the Indian Ocean. That's how we conclude. We looked at the internal variability and how internal variability is generating. But the energy budget analysis shows that baroclinic instability is the primary cause of the internal variability, and the modulation of the isothermal tilt associated with the vertical shear of geostrophic currents results in strong baroclinic instabilities. And this slowly growing baroclinic instabilities matches the scale of Rossby waves and they propagate westward carrying the energy. That's it. Thank you.
Very nice analysis. Any questions for Anjana? Yes.
Hi, Anjana, it's a nice talk. So I just want to know, like, these two regions that you have shown on your map. So one is a Lewin current region and one is the Agulhas region, right?
Yes.
So they often having a very large shedding of the eddies, right?
Yes.
So how you are describing it as an internal variability but not the eddy field?
Because all these things are we did from like climatological simulation, and if we remove the annual cycle, whatever we are getting is basically from the internal variability. So
I doubt, because they are the permanent region for the eddies, right? So eddies are there throughout the year. So that is what like shown in your baroclinic instability and the eddy kinetic energy, right?
but actually that is because all these figures are mainly from that climatological simulation, right? So in that climatological simulation, it is only that annual cycle. So if you remove annual cycle, whatever we are getting is basically
I agree that you have removed the annual cycle,
Yeah.
but they are the permanent region for the eddies. The
Okay.
eddies are there permanently for throughout the years.
Okay.
So I'm not sure like what to call as the eddy field and what to call as the internal variability.
Okay.
Okay, but anyways, nice talk. Thank you.